Hi guys, this is Kate and this is the third video for week 1 of Math 23b. Let's now talk about some of the useful theorems about Riemann integrals. For a lot of you this is going to be review, but remember that you learned about Riemann integrals in a univariate class, at least in R, so this is a more generalized functions. We're dealing with two functions, f and g, that are integrable functions. Remember that means that their upper and lower sums converge as the level of dyadic division goes to infinity, and they map from Rn to R. So they might have a ton of inputs, but they have just one real number as their output. So if we have two integrable functions, then the function f plus g is integrable, and the integral of f plus g equals the sum of the integral of f and the integral of g. And in fact, this is going to be your proof 14.1 for proof logger. The next one is saying that the integral of alpha times f, where alpha is some constant, equals that constant times the integral of f. That can be rewritten as such. And then last but not least, if f, the function, is less than or equal to g, the function, everywhere, then the integral of f is less than or equal to the integral of g. Note that if n equals 1, if we just have functions that map from R to R, we can calculate Riemann integrals by using antiderivatives, just like you learned to do in single variable calculus. No big deal. Even when we get a little bit more complicated, where n is something other than 1, no, we can't use basic antiderivatives, but you'll see, life is not over. It's quite doable, and that's going to be the focus of some of our later units past this week. Note that there's a product rule, which says that if you have one function that's just a function of x, that's integrable on Rn, and note that this x is a member of Rn, it has n different components, and there's a second function that is a function of y, and y is an element of Rm. It has m different components in it. Then g, which is a function of both x and y, which is equal to that first function of x times that second function of y, that's going to be integrable on the space Rn plus m. So you add that dimension together, and the integral of g equals the integral of f1, that first function of x, times the integral of that second function of y. Our third bullet here, fourth bullet I should say, says that by combining the above rules, we can integrate a function like x squared times sine y plus e to the x times y cubed over a rectangular region in R2. Well, what we would do here is we would use our first bullet to separate these two into the integral of the first term plus the integral of the second term, and then we note that we have a function of just x times a function of just y plus a function of just x times a function of just y, and note that we can separate that by our third bullet here into the integral of the first function of x times this integral of the second function of y. And then once we have that, we have two integrals that are just going to be in R, so where n equals 1, and that second bullet comes into play, so we would just calculate them by using antiderivatives. You'll see many examples of these being computed later in the course. But this written out is what we would do to that first term. Note that we start, if we're integrating this function over a rectangular region in R2, that means that we're integrating with bounds with respect to x as well as with respect to y. Since I don't really know which order I'm going in quite yet, I'm going to put dA there. And then we can say that the integral of the product is equal to the product of the integrals. That's only because we have a function only of x times a function only of y. That's why we can separate them. And so we end up with just the integral with respect to x for the function that's written in terms of x times the integral with respect to y times that function with respect that's in terms of y. Remember that if you have a product of two functions and they are not strictly a function of x and a function of y, you cannot separate them like this. We also have this following property here that says, given our definition of the integral in terms of dyadic cubes whose endpoints are rational numbers, it becomes a provable theorem that if a and b are any real numbers with a less than b, then the integral from a to b of, note that this is really the function 1, it's just not written there, it's 1 times dx, is equal to b minus a. And this looks like new notation, this absolute value. That's something that Hubbard uses in the textbook, and it's very nice. This basically means that orientation does not matter. There's really only one orientation that makes sense. We'll talk about when orientation matters later in the course, And we'll introduce it slightly at the start of lecture, but what we're saying here is that the length of the interval is given by integrating 1, so we get b minus a. And from the product rule, it then follows that the area of any rectangle equals its length times its width. So that is going to be your proof 14.2. It's a very handy proof, and we'll go through it in depth in class this week. Some of the tools that we'll be using while we're exploring integration will be introduced this week as well. So what's interesting is the volume of a region, and we're going to name that region A. It's a subset of Rn, is defined as the integral of an indicator function, which is 1. It's written as a bold 1 with a subscript a. And this indicator function basically is equal to 1 when you're at a point that's in A, and it's equal to 0 for points that are outside A. So basically what we want to do is we want to integrate the value 1 over the region A to find the volume of that region. We'll be doing that later in the course as well. This volume remains the same if we translate A by adding a fixed vector to each point in A. So the unit square has the same volume whether it's anchored at the origin or it's anchored at 2, 2. We also note that if A and B are disjoint sets, the volume of their union is the sum of their volumes. And so if their volumes can be written as the integral of indicator functions, we're going to end up using the indicator function for A union B is going to be the indicator function for A plus the indicator function for B. We're going to go through exactly how this is true, and later in class we're going to see how by reasoning through this we'll then be able to prove the original statement that the volume of their union is the sum of their volumes if they are disjoint sets, which means that they don't overlap, they have no points in common. And last but not least, a bounded continuous function is guaranteed to be integrable over a bounded region in Rn. This is a generalization of a theorem that you've probably already heard in univariate calculus that says if you have a bounded continuous function over a closed interval, it's integrable. So that's probably not news to anyone. Now let's take a look at some applications of integration. You'll be exploring a lot of these on your small group problems as well as on your homework assignment.